Ladies and gentlemen, welcome to the final plenary session of this year's EAC. My name is Joachim Pogels from Lund University in Sweden. I will be sharing this session together with Professor Vladimir Štimal of the Czech Academy of Science. We are honored that Professor Tunga Salthammer from WKI Braunschweig in Germany has accepted our invitation to give a plenary talk. The title of his talk is Characterization of Residential Indoor Aerosols and Their Sources. Professor Salthammer studied chemistry at TU Braunschweig. After completing his studies and receiving his PhD, he joined Fraunhofer Institute in 1990 as a scientist, where he is currently the deputy director. Since 1995, he has been the head of department for the Department of Material Analysis and Indoor Chemistry. In 2008, he habilitated at the Faculty of Life Science at the Technical University of Braunschweig. He holds and have held several guest professorships at the leading research groups in the indoor air quality and indoor aerosol areas, including Technical University of Denmark, Tsinghua University in China, and Queensland University in Australia. His main research topics in the past few years have been indoor chemistry and particle emissions from laser printers and emerging new particle sources such as electronic cigarettes. He lately published a paper about the indoor emission from fireplaces. He also studies formaldehyde in the indoor environment. He is first author of a paper in Chemical Reviews that has been cited more than 200 times. He investigates gas and particle distribution of semi-volatile organic compounds and also very lately the dermal uptake of phthalate esters. So we are very happy to introduce Professor Salthammer.
Thank you very much. Good morning. And I hope you enjoyed the dinner yesterday, and I did it. And many thanks to the organizers to host us in this wonderful ambiente. And very pleased for the invitation to give this plenary here. To be honest, I was a little surprised, but was honored. This is not my usual playground. I've been to aerosol conferences a couple of times before, and really appreciate that because you have time to listen what other people are doing and just learn. So thank you again for inviting me. Don't be afraid, I will not going to talk about formaldehyde today. This molecule follows me for over 25 years now. My topic is relatively broad. I will give you an overview what indoor scientists are doing. I know there is some indoor science here, but I also learned during this conference that many of you are not involved in indoor sciences. So let me give you an overview what indoor scientists are doing. I felt free to modify your logo a little bit and do house. Well, how does this work? Yes. What I'm going to talk about, I will briefly introduce you to the fundamental of indoor sciences, what we are doing, how indoor scientists work. Then I'll turn a little to the indoor particle dynamics, indoor and outdoor relationship, and then particles from indoor chemistry, start with the sources, and then, as the chairman said, some indoor sources with a focus on laser printers and other electrical appliances. We'll talk about combustion sources, other indoor particle sources. There are many of them. There are really plenty. And a little bit of about particle exposure, which is not really my field. I'm a physical scientist. And finally, I will give you some kind of warning I've done earlier here, how gas particle distribution of SVOCs is used and misused for exposure estimation. Well, indoor sciences work, or let's say in my field, we have many. I saw biological. I do not care about biological contaminants. We deal with molecules, VOCs, SVOCs, and particles and their interaction. And for practical reasons, indoor scientists classify organic compounds by boiling points. We start with the very volatiles, the VOC, which are boiling points usually below 60 degrees. Then we come to the probably most important groups, VOCs, SVOCs, the semi-volatiles, and finally the POMs, the particle-oriented matter. It's important that there are always misunderstandings because atmospheric scientists and indoor-related scientists, we have no POPs, no POPs. And also our definition of VOC is completely different to the outdoor world. VOCs are clearly defined now by the indoor community. There are ISO standards on this. We are very happy that we finally have this definition, which is based on the gas chromatographic retention times. Why do we classify these compounds? Because we're interested how they are inhaled. Are they in the gas phase? Are they attached to airborne particles? And do they find in the sedimented house dust? And this is of important if it's inhaled or it's taken up orally by ingestion or whatever, or via the skin, dermal uptake. Well, what are indoor-related chemicals? We deal with about, including tobacco smoke, we deal with 5,000 to 10,000 different chemicals. So in our lab in Braunschweig, I'm not very sure about this. One of my colleagues knows much better. We have standards for about 2,000 chemicals we are frequently analyzing. About 900 of these are important. So this is my classification now. There are different kinds of organics. We have the so-called classics, known for a very long time, which is, for example, toluene and butyl acetate, just to mention two. And then we have what I call the avant-garde. You can think who this is. We come back to this group later. The avant-garde are modern chemicals we are dealing with. This is the modern plasticizer here, this one. This is called DINCH, established in 2002 to substitute phthalates, or the upper one is squalene. There's a lot of chemistry on this molecule, chemical research on this molecule. And finally, we have something what my colleague Charlie Wechsler, I think is well known also in this community, called the stealth chemicals. Chemicals that are found in very, very low concentrations, difficult to identify, but they are important due to their health effect or to their odor effect. And just to mention a few, this is an unsaturated alcohol here. It's a metabolite from fungi or OPA, or this is the cyclic ether here. Well, this is like indoor chemistry or indoor analysis, like a detective's work. Well, what is our world? Our world is the indoor environment. This is the one, and usually we work with sources, any kind of sources, and this emits something. This is the molecule. Say hello, okay, and then this emits from the source, and then usually it is in the gas phase. So what can happen then? From the gas phase, it can be exfiltrated via air exchange rate, then it's out. It can be deposited in a sink, usually the wall, or it can be attached to particles, or it can be deposited in the settled dust. And this triangle here, gas phase and particle phase and dust phase, this is indoor-related exposure. This is, of course, not the full story of exposure. There are lots of other sources for exposure, ingestion or other, but this is what we understand by indoor-related exposure research. Well, how do indoor scientists work? It's very similar, I think, to what outdoor chemists or atmospheric chemists are doing. We work in the field, of course, in real rooms, but we also work with chambers. We have very big chambers, as you can see here. This is our biggest chamber. We have a stainless steel chamber, commercial type, 48 cubic meters stainless steel, but we have also micro chambers. So our chamber size, depending on the materials where we are investigated, the smallest one we have is cup size. And therefore we classify our chambers in the large scale. Large scale means you can walk in. The small scale chambers, let's say between 1-2 cubic meters and 20-30 liters. And finally, we come to the micro scale chambers and the cells. And what you see here is an important tool where indoor scientists are using. This is a cell. There's also an ISO standard for this cell. This is like a chamber, but it has no bottom. And it is to investigate the emission from plane surfaces. So you can put it on this parquet, for example, and then you can flush air through, and then you can measure the emission from these kind of surfaces. And the equipment we are using is usual. We have GCMS, we work with HPLC, we work photoacoustics, PTRMS. I love PTRMS, for example, for in chamber testing for identifying organics. And we also work with all types of particle counters. You see here the GRIM, and this is FMPS. I prefer the FMPS, not because of the technique, because of the size of the time resolution. We work with many processes that require a very, very high resolution of about 1 second. And this is the classical instrument here, the SMPS. You know this very well. So this was the introduction, very briefly, how we work. And now we come to the indoor-outdoor dynamics of particles. And as I have borrowed this and a little bit modified from a very good paper from the 90s by Thatcher and Layton, published in Atmospheric Environment, there are many sources, or let's say processes, generating particle indoors. Of course, first you have the contaminants outside, and you can bring them in by tracking or infiltration. Tracking is very important, especially in the case of kindergartens. I wonder who knows how many particles are brought into the environment by kids playing in the kindergarten, walking inside, walking outside, and then the dust they're bringing is resuspended, or they're bringing the particles and then they release the particles indoor. And they can be infiltrated via the air exchange rate. Then they can, of course, be exfiltrated by air exchange, by cleaning, or by filtration. But sometimes the filtration also produces particles. This is also possible. And then they have different kinds of, let's say, fate. They can be deposited by different mechanisms. They can be generated in the environment. We'll talk about this later. And they can, of course, be resuspended. So if you're interested in any details, I can really recommend this paper by Thatcher and Layton. Well, what dynamics is important for an indoor scientist? There are plenty. Of course, gravitation, deposition by gravitation, and the resuspension. There's a lot of work on the resuspension of particles, depending on the size of flooring. On a parquet, which is very elastic, there's a lot of resuspension, or carpet accumulates a lot of particles, lots of dust. Then, of course, we have the diffusion processes. And finally, what is really of major importance, unfortunately, very often underestimated, is thermophoresis. And why is thermophoresis such an interesting topic? Because there are lots of large temperature gradients in the environment. Usually, or in older buildings, the air in the environment is warm, but the walls are cold. So you have an airflow from the air to the wall, and then this transports particles, and these particles are then deposited on the walls. I will explain this later in more details when we talk a very special indoor topic we call the black magic dust phenomenon. Well, this is let's say the fundamental equation of indoor-outdoor particle dynamics, and this is, I think, the most complicated slide I will show. This is by Bill Nazaroff. Bill Nazaroff also published a very nice review, 2004, in the Indoor Air Journal on indoor particle dynamics. And there are plenty of mechanisms. This is leakage. This is infiltration of leakage, and this is a penetration factor. It's very important. What is the penetration factor? If you have particles outside, you would like to know which particles penetrate indoors. Then usually this is the air exchange. Leakage and air exchange are different worlds. I will show this on the next slide. And then you have mechanical ventilation here. Or this is the outdoor particle concentration. And sometimes you have air cleaning devices in the indoor environment. Not always. This is very rare that you have both mechanical ventilation and these, but sometimes you have standalone air cleaning devices, and this filters off particles. This is the particle loss rate, better in the indoor environment. E is an indoor particle source. V is the volume, and finally Ci is the indoor concentration of the particles. And this is, as you can see, the fundamental equation, balanced equation, when considering all these processes. Usually you must not consider all these processes, and this equation can very often be simplified. Well, I said particle penetration from outdoor to the indoor environment is important. This is difficult to measure. Well, some people have tried to model this, and this is also in the paper by Bill Nazaroff and in his review. It's interesting. How do particles penetrate from outside inside? And this is a calculation. This is just a modeling penetration through a crack. The crack is here 1 millimeter thick and 10 centimeters in length, and Bill Nazarov has estimated a pressure gradient of 4 Pascal and a density of particle density of 1 gram per cubic centimeter. And you can see here for this, as expected, of course, that in this range here, let's say between 30 nanometer and about 5 to 3 micrometer, the penetration of particles is very high, exceeding 80%. This is a model. This is roughly estimated, but it works very well. And the experiments show that particle penetration, experimentally determined penetration rates, are in the same range, or let's say a little bit lower. But that you have to expect. And this is no surprise, of course, because this is the inverse, more or less the inverse of the particle, the deposition rate, you know very well. Well, I said at the beginning, there's a difference between air exchange rate and leakage. And this is very important for Indoor Sciences. Air exchange rate is determined by using a tracer gas, spiking the indoor atmosphere with a tracer gas, which is often carbon dioxide, but it's also N2O or SF6 or so, and then measuring the decay, which is usually exponential. But then there's another test where you put the house under overpressure or under pressure, and usually use 50 Pascal. This picture here determines overpressure, and you determine the airflow that is necessary to establish a constant overpressure in this house of 50 Pascal. And if you know the volume of the house, the volume of all the rooms, you come out with this so-called leakage or ACH rate. 50 refers to the 50 Pascal over under pressure, and this is another important, very important parameter. This is called the blower door test. I'm not sure if you're familiar with that. In Germany, this is required to do a blower door test before selling a house because of the heat and the air exchange. We have now laws for this. And a very nice paper also by Stevens and Siegel has investigated the influences of particle penetration on the air exchange rate and on the leakage rate. And we define a so-called outdoor source term, which is the penetration factor. I will not go into details here how this factor is determined. This is really sophisticated. Stevens and Siegel have used a very, very good method for reliable estimates. You need to measure particles inside and outside, and you need to determine the particle loss rate, and so on and so on. But finally, the outdoor source term, particle penetration rate multiplied by the air exchange rate as determined with a tracer gas, correlates nicely with the leakage. They have done this in 18 houses, and this is the best study I know so far on this topic. Well, there are many more parameters they have determined, but it's very simple. It is also no surprise that the higher the leakage, the higher, of course, is the penetration. And you see here, if the leakage is very low, you have very low penetration factors, and here with high leakage rates, you exceed 0.6 and you come out to 0.8, close to 0.8. Well, and this is also interesting that this is quite funny that the outdoor source term could be related to the year the house was built. And this is clear, but it's a nice picture, and I wanted to show you this. As an older house is not so very tight, and the correlation is not so very good, but it is a clear correlation. The older the house, the higher is the leakage rate, and the higher, of course, is the penetration factor into the house. This is tight houses are good and bad. We have today lots of heat insulation, of course, a low penetration of particles, no leakage. But on the other hand, we need air exchange, and it will be a future problem how to achieve this airflow between the indoor and the outdoor environment. Well, That's all for so far for particle dynamics in indoor-outer relationship. And now we turn to particle sources in the indoor environment. And I will start with indoor chemistry. There's now plenty of work in the indoor environment on reactive species. Ozone has been frequently studied in the environment. There's a nice paper by Charlie Weschler, again, Indoor Air 2000. And hydroxy radicals, NO2, and so on, even HONO, very recent work about HONO, not just yet published in Journal of Photochemistry and Photobiology 2016. But it's available in the databases. So you can see that these concentrations of these reactive species can be very high. And I heard yesterday that Xavier has identified more than 200 ppb of ozone in an indoor environment or so. This is very high. That's a very high value. And so on. And we also, so it's a myth that many people say there's no ozone in the indoor environment. This is not true. A lot of ozone is coming in from outside, and we have plenty of ozone sources in the indoor environment. I will also show you that later on. And moreover, we also have PAN in the indoor environment. There's a paper from the 90s by Jacobi and Fabian. So all these papers present very good work on these reactive species. And then we have very high concentrations of terpenes. I have two examples here, the limonene and the alpha-pinene. We bring in by wooden furniture, but also we have plenty of other sources. So you can imagine that a lot of interesting chemistry is going on in the indoor environment on terpene and ozone and hydroxy radical chemistry. It's the same outside, but the concentrations are higher. And I would like to say that the particle that the particle formation in the indoor environment is much higher compared to the outdoor environment. Well, this scheme is very well known. This goes back to Kriege. There was a chemist from Germany, I think he was from Karlsruhe, and he has established a mechanism how unsaturated hydrocarbons react with ozone. I have simplified this a little bit. We start with the terpene here, the alpha-pinene, and then the ozonide is formed, and the very famous Kriege intermediate, the biradical, and then oxidation products are produced. And these oxidation products can condensate and form larger molecules by polymerization. And then finally, you come out with their nanoparticles. And this mechanism is now very frequently studied in the indoor environment. Well, the kinetics is rather sophisticated because we always work with materials. So this is the material here, maybe a wooden shelf board full of terpenes. Pine, for example, has a lot of terpenes and emits high concentrations of terpenes. And then we have the ozone here coming in from the outer environment. And then this material could emit terpenes, and they have the gas phase reactions here. And these products may remain the gas phase or may form the particles. But on the other hand, we also have the surface reactions product. We have the reaction on the surface, and then the reaction products might emit into the indoor environment, and so on and so on. And of course, ozone is not very stable in the indoor environment. There are lots of losses, and you also have to consider this loss term here if for the ozone reaction. There's plenty of work on this topic. This is not only gas phase reaction, that I want to say here. This is how we did some experiments. This was at DTU in Denmark in 2008. This is Charlie Weschler, and this is our student Sarah. And this is our 2 cubic meter glass chamber, and you can see here the wooden shelf boards inside, and we have purged the chamber with ozone under certain conditions, a defined temperature, of course, and a defined air exchange rate. And then we have measured the ozone, we have measured the VOCs, we have measured the particles, and I will show you only one typical picture You can see thousands of these in the literature. This is the ozone concentration here, and we kept this constant on the level of 20 ppbs. 20 ppb. This is the count medium diameter here, the red one. And when the experiments start with the gel, the ozone consumes the terpenes and then starts producing particles. And then these particles grow. And from about here 40 nanometer count median to about finally 100. So it's very typical. So the typical outdoor chemistry is also going on in the inner environment. And then later the particle concentration decreases for two reasons. First, the particles condensate; they're getting bigger, and the terpenes in the chamber air and on the surface are more or less consumed. Not all pictures look like this, but this is a very typical picture of indoor terpene ozone chemistry. And if you're interested in that, this is published in Atmospheric Environment in 2008. Well, there are plenty of other sources, and I would like to show you some of my favorites. I hope you can read it. This is room freshener here, and these room fresheners are full of terpenes, especially limonene, and this is one of my favorite here. This is, I'm not sure if you can see that. This is a little dragon. You can buy this as esoteric shopping if you like it, and you put some oil here, and you put a candle in here, then you evaporate the oil, and you have all these oils in all the oil ingredients in the atmosphere, and then a lot of reaction is going on. Very nice paper by some French colleagues. And this is famous work by Nazarov and colleagues, Beverly Coleman from Berkeley. They have studied many of these cleaning agents in the chamber in the presence of ozone. The ozone concentration was a little bit high, but the kinetic studies we're doing are very, very good. This is paints. This is a work, Journal of Hazardous Materials by Lamorina et al. And finally, sounds strange, but it is true that even particle removal generators produce particles. This is no joke. They on the one hand, they remove the particles in the air, but many of these produce unsaturated hydrocarbons. They emit unsaturated hydrocarbons into the indoor air, and these unsaturated hydrocarbons react with ozone. So on the one hand, you're removing the these devices remove the particles, and on the other hand, these devices produce particles. So this is also very good work by Michael Waring, and Jeff Siegel and Rich Corsi from Austin, Texas, are also published in Atmospheric Environment. There are many more sources, of course. This is just a selection of few. This is my highlights. Well, I previously showed you this group, and I'm not sure who's, let's say, experienced enough, or like my daughters would say, cool enough to remember these people here. This is the Velvet Underground. Most of them are dead, unfortunately. And I'm very sure that some colleagues, why I'm showing this is a very famous record, this banana, and the covers by Andy Warhol, and the slogan on this is "Peel slowly and see." And I'm very sure that some colleagues from Finland were inspired by this album. What have they done? They have peeled oranges. And first we only have to substitute this banana by an orange, and an orange emits limonene, and this is exactly what these people have done. This is their paper in Atmospheric Environment 2006, a very good and very funny paper on the formation of GROW. I'm not sure if you can read it. We released D-limonene into the room by peeling oranges and measured the concentration of aerosol particles of 3 different size ranges. And you can really see that just peeling an orange produces lots of particles. And the particle concentration, this is the start of the orange peeling here. and then particles go up and then go down again and then raise. It's a very nice paper. I know that Lilia Moravska has done the same. That has a very nice video, but unfortunately it's not available in the internet, showing somebody peeling an orange, and then there's a particle counter next, and you can see the particle concentration in the environment growing to really high concentration. So this is another source. So it's, of course, this is not so very serious, but it shows that there are plenty of particle sources in the environment. This is a picture taken by Charlie Weschler on a restroom in downtown Copenhagen. To make one point clear, this does not mean that my good friend Charlie Weschler can be frequently located on public restrooms, but he took this picture, and this is an ozone generator here, and this is an air freshener. So, and I have more or less stolen this paper from him. He's showing this very often, and he gave me permission to use it for my presentations. And this is a big mistake to do this, because this will produce a lot of particles. Maybe it's not so important on the public restroom, but it is also frequently done in the indoor environment. Ozone generators are now more and more used. You will see it on one of my last slides. Well. Let's go to another topic. This is indoor chemistry, and we now turn to electrical appliances. This is a picture I've taken from the Moravska group, from a paper by Kong Rong He and colleagues in ES&T, published in 2007, and this shows the particle concentration in office room in Brisbane. And then you can see here, during the night, there's a low concentration. This is outdoor, this is indoor. And in the morning, early in the morning, when people come to work, the particle concentration increases, let's say, dramatically, yes. And then later at 6 p.m., the particle concentration decreases. And this is due to the use of laser printers, or this was due to the use of laser printers. And this study triggered a big discussion, I think all over the world, how laser printers affect your health and whatever. And we have done plenty of experiments on these laser printer stuff. These are some impressions from the QUT. This is Kong Rong He, this is me, when we are doing this experiment. This is our lab at WKI. My colleague is setting up the experiments for the laser printer emission. There's a defined protocol. I will not go into details here. This is the printing protocol for a color printer. You have to do it in 10 minutes, and so. And the interesting thing was that we have different chambers, and our equipment fits together. It fits nicely together. They have a flow-through chamber here, and we have a well-mixed chamber. And so this makes sense. We brought many printers from Braunschweig to Brisbane, and from Brisbane to Braunschweig, and investigated these in both types of chamber. And every printer is different. This is an interesting thing. This is the red curve is the chamber concentration by time. So the printing is always 10 minutes here. You can see this. And then there's, of course, an increase and there's a decay. And you can easily apply a mathematical procedure called deconvolution. And then the blue one is the emission profile of the printer in particles per time unit, second or minute, or probably second. And if you compare these blue curves here, you can see that all are different. So you can never sure how your printer emits. We call this type here an initial burst printer, and then there's nothing. This is more or less a constant emitter here, and we have printers that emit in intervals, and then we have this is also more or less a constant. The constant emitter. I think we have tested and investigated a whole variety of printers you can buy on the market, and we know what many of the reasons for how what are the reasons for which type of emission profile? Well, but as I said, I will not go into details. What is very important, what is the chemical constitution of these particles? Many people think, and it's wrong, that it's toner particles. There are no toner particles. A typical laser printer does not emit toner particles. No carbon, no iron, or very few solid particles. There's also typical condensation dynamics going on in this printer. This is a profile. This is a typical printer profile here. The tower plot, starting with very, very low particle diameters, so let's say about 6 or 10, and then slowly the particle size is growing. It's almost a banana shape, like not really, but very similar, but banana-like shape. Well. So the question remains, what are these particles made of? And we have all done a lot of work trying to identify. And the solution was very simple. This is just one sampling techniques we are using, and then we've applied GCMS and scanning electron microscopy with X-ray analyzers. So this is a little bit small here, I'm afraid. This is very typical for the printer particles. They are waxes, more or less waxes. Hydrocarbons starting at C30, C20 until C45. There are lots of siloxanes which are used in these printers, and they make more than 98% of the particles. These evaporate under thermal stress. And there are also very few, sometimes we could identify iron here, but this makes altogether less than 2%. So these particles are volatile. There are these waxes, but no way, there are no toner particles. There's no iron. There's no nickel. More or less the waxes and the lubricants they're using in these devices. As I said, there's a big story on these printer particles all over the world, especially in Germany. This is a very nice cartoon. I will not tell you about the microwave popcorn story now. This is a completely different story and takes too much time, but I love this. I really love this cartoon. Well, did I miss one? Sorry, I'm a little bit confused. Maybe later. There are many other sources in the environment, and one of these is combustion. We heard a lot of work here, very good work on combustion. But what is the impact of these devices on indoor air quality? And we have worked on two kinds of devices. This is the typical the oven, which is used for heating. It's becoming very popular in Germany now. And this is special, has no practical use. This is an ethanol-fired device just to produce some well-being. When you burn it, when you look inside, you feel better. So, okay, if you like it, but this is the point is these are regulated by law. These the wood-fired ovens. The purpose is heating, and they are vented. And we have done measurements in real indoor environments. And this is the main purpose of this is decoration, and this is non-vented. So all the exhaust goes into the indoor environment. And we have done some room size chamber measurements. This is for the wood oven, and there are particles, of course, especially when you open the door to refill, to put some more wood in, and then this is done by an FMPS. You can easily see the peaks here, and the concentration is going down and then going up again, and then you have definitely an exposure to particles. There are many other compounds. The strongest source, by the way, was benzene. I will not talk about it, but the benzene came from the lighter. You usually use some of these little white cubes for starting the fire, and some of them have a high content of benzene. And this is the typical particle concentration here you may expect in the indoor environment from this wood oven. This is me. As you can see, this is my oven. I was one of the subjects for investigation. And this is the ethanol burning fireplace, and to make it short, this was terrible. They emit lots of particles, very high concentration of particles, more or less. We have tested different devices. This is done in chambers, but under very realistic indoor conditions in a 50 cubic meter chamber. And there are lots of other emissions except the particles. We have these fine particles, but we have very high concentrations of formaldehyde and other organic compounds. So everything you can expect from ethanol combustion. There's plenty of work on this. If you read that, you have everything in the environment. So I cannot really recommend this for indoor use. Well, to summarize this part, there are, of course, as I said, many other sources. I just picked a few highlights with very good papers behind. This is nanosprays, for example. It's a nice work from Denmark, Norgard, and which is from the group of Peter Volkov in Copenhagen. Then we have many other household devices. So after this presentation, your life will probably change. When you go home tonight, or when you use anything, a hairdryer or a toaster or whatever tomorrow, you will always be to think about particle exposure. So each of these devices emit more or less particles. And then cooking. I've taken this from Giorgio Buonanno, who explained me a couple of years ago how to make a good pizza. And there is good and bad news for the Italians here. You're probably making the best pizza in the world. Nobody will seriously doubt that. But in this case, you have to accept particle exposure. So this is very, very simple. But it's not so bad. I would like to cite what the WHO says. Well-being and health is not necessarily related to the absence of pollutants. So if you have some well-being and you feel good, and then you can easily accept some particles from pizza making. And finally, a big story now coming more and more into the literature, electronic cigarettes substituting the conventional cigarettes. There is lots of work and lots of studies done on these cigarettes. So if you want, you can read all these papers behind. I would like to close this part with a paper by Christian Isaksson from Sweden. She has recently published a review or a study in atmospheric environment, and this group has summarized many of and ranked particle sources indoors, and of course the combustion are the highest emitters, starting with candles here, smoking, oven, and then cooking, frying, toasting, ironing, cleaning, and so on. And the last one here is open windows, so outdoor sources. And I found an interesting statement in this paper saying the majority of airborne particles in residences, when expressed as number concentration, non-mass, are generated by the residents themselves. So most of the particles you find in indoor air, you produce them. Well, let me talk about 5 minutes about black magic dust, or what we call black magic dust in housings. I'm working on this field, unfortunately, for almost 15 years. I'm often called by dwellers, by consumers, that their apartment is going to be black. And this is a typical example here. This is a heater, and then you can see these black stripes. And here's another one. I hope you can see that. I have zoomed this. You can see this black curves here going around this one here. And the question is, what is the reason for this what we call the black magic dust? This is not new. This is old. This phenomenon was described many years ago by Nazarov and Cass in an atmospheric environment paper. It goes back to 1991. Or it was also investigated by Camufo from Italian for soiling in museums. Why I show you that? This phenomenon is often called fogging. And this is wrong. This phenomenon has nothing to do with fogging. Fogging is the condensation of SVOCs on surfaces. And here, this is the condensation, or not the condensation, sorry, it's the deposition of particles on surfaces. So I would always call this phenomenon soiling. And there are lots of studies on that. The questionnaires, and this is more than 90% this occurs during the heating period, occurs in winter when the doors and the windows are closed and air exchange is comparatively low. And there are, as I said, lots of studies on that. And the reason is very simple. This is most of these are caused by thermophoresis. This is a thermographic image here. And this is not the dust. This is the airflow here. This is the temperature. You can see that this particle deposition here nicely follows the airflow. And I even have a better picture. Unfortunately, the video doesn't work, which is thank you Windows. There's a codecs missing, so I had a very nice video showing how the temperature profile above this heater develops when the heater is turned on. So I finally can only show you. I think this will not work. No, unfortunately not. But I can show the final result. And when the heater is turned off, this temperature profile develops, and you can see that this pattern and this, which is temperature, and this, which is the dust, are overlap or more or less perfectly. So this phenomenon is clearly triggered by thermophoresis and concentrations of relatively high concentrations of particles. Well, this is the final outcome of this Blatchley dust. The phenomenon I was talking about is this part here, the sudden dust deposits. Of course, there are other sources in the indoor and in the outdoor environment, which is just combustion or black carbon. Candles. If you burn 50, I've seen people burning 100 candles in their apartments for reason I do not understand, and then of course your apartment will turn black. Then you produce a lot of SVOC, you produce polycyclic aromatic hydrocarbon soot, and so on. And sometimes it comes in through the heat and ventilation air conditioning system and diesel soot and so on. But this is a different story. This is simple carbon deposit. What I was talking about is this part here, sudden deposits, usually caused by thermal bridges, cold walls, hot air or warm air, low air exchange, and then some primary sources, and then temperature gradients. Well, couple of minutes on the indoor exposure to particles, which is, I said, this is not really my business. You have seen this picture before. It's a very famous picture from the ICRP, the publication. If you do that, this is frequently done in the indoor environment. You need to know about the chemical and the physical properties of the particles. You need to know about gas-particle interaction. You need to model uptake of particles in the respiratory tract. And there are lots of in vivo and in vitro studies. For details, I could also recommend two papers, one by Werner Hoffmann from Austria, from Salzburg. He has modeled the particle disposition in the lung. For me, as a non-expert, it's a very, very good paper. And then a recent review paper by Muravskar and colleagues on indoor aerosols from personal exposure to risk assessment. So I would like to highlight one study, and this is the uptake study from Australia. I've received this picture from Sam Clifford, who was at WKI for the last couple of weeks. And this is an interesting study. Not the only study, of course, but it's interesting. I would like to highlight it here because it covers both the indoor and the outdoor environment, and they have followed the kids for 24 hours. And this study nicely shows what are the sources for particles. When you follow these kids, you can see it here, how many hours are spent at school indoors, how many hours are spent at school outdoors, in commuting, home and eating, home and sleeping, home, other, and so on and so on. And they done this for hundreds of kids, and then with this personal exposure, with this particle monitor, they followed the personal exposure to the particles. I've just picked 2 for a student or a kid with a high exposure, and here is good with relatively low exposure. So this study nicely shows us how the kids are exposed, how the school kids are exposed to particles, where and what are the sources and what are the important topics on that. This is for Brisbane environment. Might be different for other regions, other parts of the world. Well, the paper is by Mandana Mazaheri and colleagues, published in ESNT. And this is also interesting. This is a story, a paper or a work by Peter Volkov and his colleagues. There was, if you say, terpenes. This on terpenes and limonene ozone reaction. So people said 10 years ago or 15 years ago, there is no ozone in the indoor environment, there is no indoor chemistry going on, and terpenes do not cause any problems. And Volkov and colleagues have done a very nice story. The simplest parameter you can measure is the eye blinking frequency, and this is what they have done. They have done many more, but I want to show you this. And they have exposed human subjects to clean air first, then exposed to the pollutants, and then again exposed to clean air. And I just want to show you the results. First, they exposed it to ozone. Blue is clean air, and red is the exposure to ozone, and then clean air again, and the ozone was 40 ppb, and there was almost no reaction. But when you expose the humans to a mixture of limonene and ozone, you have a clear effect here. The eye blink frequency is going up. It says that people are having stress. And then finally, they have exposed it to limonene. After that, the blink frequency is a little bit higher now, about 116 ppb, which is a high concentration. And this, by the way, 31 and 75 ppb, this is possible in indoor environment. This is very, this is quite normal. And this was the first. Or one of the first studies in indoor environment showing that people who are exposed to terpenes and ozone do not suffer from one of these, but they're suffering from the reaction products, the oxidation products, or the particles. Yeah, 2 minutes. I'm almost through. Finally, this is the warning I've already given last Monday. What indoor chemists, I must say, that are doing wrong is applying models from outdoor chemistry that are not really made for indoor chemistry, and one is gas-particle distribution. Gas-particle distribution, according to Junge and Pankow equation, is very good for global transport. Very easy. You just need a TSP, the total suspended particles, and the particle distribution constant, and then you need to measure the particles in the gas phase and the particles attached on the compound, attached to particles and the TSP. And then if you have the saturation vapor pressure here like this, then you come out with that, let's say in case of DHP, which is a less volatile phthalate ester, almost 85% are attached to particles and 16% in the gas phase, and then you can calculate the inhalation via gas phase and particle phase. You can do it for a more volatile phthalate ester, DNBP, and then you have it the other way around. But this brings a lot of problems because the parameters or the vapor pressures and also the octanol air coefficients for these compounds, and this is trivial what I'm saying here, are not very well known. They spread here many decades, so these Kp values you're measuring are not very precise, not very secure. And so the final outcome is this: if you have if you take the vapor pressures for DHP, 10% means there are 50, 60 values measured. 10% of these are lower than this value, and there are different particle concentrations. You can come out and make it short with particle attached ratio between 100% for this concentration here and 20%. So be very careful when doing these estimations for gas-particle interaction, and always remember that the Junge equation was not developed for the microenvironment, it was developed for global transport. Okay, I will close. I have no conclusion. I have something about the future. What are the future challenges? Modern houses will be constructed more airtight. This is true. This is our Reichstag, wrapped by Christo many years ago. And we also have the problem that the outdoor air quality decreases, especially in the urban areas. On the other hand, we have lots of regulations for the indoor air quality. This means the indoor air quality increases, especially in the developed countries. So the future, what will the future about ventilation, indoor-outer relationship? Should we close our houses and only use mechanical ventilation? And this is exactly the question I leave open for this. There are lots of processes in the outer environment. There are lots of processes in the indoor environment. They are more and more under control now. And the point is, how will this air exchange will be done, especially in urban areas in the futures? And the final question is, how will our houses be ventilated in the future? Well, I also need to thank many, many people. I had the honor and the pleasure working with. This is my group in Braunschweig, Eric Ude, who is here, some other colleagues. This is the QT people, Lydia Murawska, Godwin, and Mandaner, and Kong Rong, and Sam. And this is the people from DTU. This is Charlie Weschler here, Bill Nazarov, and some other colleagues. And finally, I would like to thank the organizer a lot or the organization for selecting my hotel in Milano, a very nice hotel with an ozone air purifier. And I took the photo here. This says, ozone proves a nature-friendly ally against threat, and so on and so on. In addition, it removes nasty smell, destroys spores, mold, mites, bugs, and guests, probably. So thank you very much for your attention.
Thank you, Tunga, for a very nice presentation. So the talk is now open for questions. Urs, please.
Urs Baldensberger, Polgens. Thank you very much for this insight into an interesting and important field. So you showed this heater and the temperature profiles and the deposition profiles. And intuitively, I would have expected the highest deposition at the coldest place. But there was the red color, and I would interpret this as the warmest temperature. Yeah. So that was actually counterintuitive to me. Can you explain this?
Yeah, I can explain this. I didn't tell it for time reasons. One of the reasons for this phenomenon is that the people during the day turn down their heater then. And then they come home in the afternoon and they put on their heating system. So well, the air is warm very quickly, but the walls are cold, especially if the house is not well isolated. So what you have seen is the airflow at the surface, but the surface is cold. And this is the reason for that. This is the problem. I didn't. You're right. You can read the paper if you're interested. In that the problem is a little bit more sophisticated than I have shown. This is more or less related to houses with an insufficient insulation, cold walls and warm air, and this triggers the effect.
Thank you. Another question? Please wait for the mic.
Thank you for a lovely presentation, important topic, indoor air. Otto Hänninen from the Finnish National Institute for Health and Welfare. In your provocative slide towards the end on the future of indoor air quality, you suggested that the outdoor air quality is getting worse and buildings are getting tighter. Completely agree. From the Scandinavian perspective, also in Finland now, new buildings are almost completely equipped with mechanical ventilation systems, and this type of development is taking place. But now being here in the lovely city of Milan and Central Europe, Southern Europe, where it is not at all so obvious that buildings can be built with mechanical ventilation systems. So maybe we could discuss a little bit about this topic, and you comment, what is your view?
Yeah. This is a very good question. I have recently published a paper in Angewandte Chemie on this. It has nothing to do with particles, but the most important topic is formaldehyde. So when you look at the formaldehyde concentrations in outdoor air, they are increasing. And then in many cases, the outdoor concentrations are higher than indoor concentrations now. And there are lots of regulations especially on formaldehyde. Different countries all over the world have different regulations on formaldehyde. France, for example, has the brilliant idea to set a limit value of 10 microgram per cubic meter, which is almost nothing. Well, in other countries, I know in Canada, Scandinavia, there is 0.05. You can easily live with that, and other countries they are higher. So this means that in the near future, especially in urban areas, if you have no mechanical ventilation, and I really don't like mechanical ventilation. I live in a very open house, but I live in a suburb, so I like having windows and doors open. But in the future, you have the problem that formaldehyde, for example, penetrating from outdoor air to indoor air, and then the indoor concentration will exceed the limit value, and then we are running into big problems. I have no idea about these limits here in Milano. In Germany, we do not have such a big problem because we now adopt the WHO value, which is 0.08 ppm. But in other countries with a very low formaldehyde level, Hong Kong is one of these. France, there are more. They will run into the future if the houses are not mechanically ventilated. This is very simple.
Thank you. I think due to time concerns, we cannot allow for another question. Please let your questions for the coffee break, because now there will be a Best Poster Award. So I would like to thank our speaker once again.
Okay. Good morning, everyone. My name is Nynne Prisle, and I have the pleasure again this year to hand out this year's EAA Best Poster Award. First, I would like everyone, if you would help me thank my wonderful team of very hard-working evaluators. So some of them are here, and if anybody else is here, please stand up and please give them a warm hand. Thanks. These guys have been working really hard during our 3 poster sessions. We've had a lot of very good posters and interesting discussions. But now I have 12 awards to hand out, and we have a small gift also. So I will read out the names, and if you would please, if you're present, come down. And if you know that the person is not here, if somebody could accept the award on their behalf, please come down here. So, let me see. The first one is Stefeng Sao. Are you here? Please come down. And Federico Bianchi. Anyone who knows Federico? Please come. And Claudia Fuchs. and Sebastian Schmidt. And Gutste Ergin. Anastasia Spirotiani. And Michaela S. And Manish Agrawal. I'm not sure. And then we have Nicholas Talbot. And Brian Bistek. And these were this year's best awards, best poster awards. So it was both, they're awarded both for their very nice posters and also for their presentations during the poster sessions. So please, let's thank all of them.
Yes.
Oh, yes. I'm so sorry we lost the last two. Pallavi Pant also. And Deep Chandra Srivastava. I don't know, you're not all. I think I can hand out the certificates to you afterwards here. I think Sabine has now also something she would like to say.
Well, actually, we are doing some awards this morning. And I think to get an award for the best poster, that's a very nice thing to get. But actually, we would like to give another award to the local organizing committee. Could at least some representatives of them could come to us on the stage? So in order really to appreciate what they have done for us, I have decided to do something which you should never do, to bring food to Italy from Germany. So I brought a bottle of my most favorite white wine. I'm coming from a wine growing area, and it's actually a very famous one. So I don't know, you have to share. And as I'm quite sure it's quite exhausting to organize such a conference, I've decided to bring a little bit of sweets like marzipan hearts and Haribo vampires, because all of us were drinking a little bit of power out of these guys here. And so I think they really did a really great job. Thank you. And last but not least, I really would like to thank all the working group chairs for doing all the scientific work in the background, all the people who helped putting the sessions together, chairing them, and of course also all the technical assistants without whose help we would not have been able to have such a great conference. And I really enjoyed it here. Thank you very much.
So you can go to the last coffee break of this EAC 2015, and after the oral session, see you again just for a while here for the closing ceremony, please. See you later.